Last class we talked about power series and how to determine where they converge. Today we're going to move towards finding out how we can represent functions that we know and love as power series. And the connection between the two will be to use Taylor polynomials. And so Taylor polynomials are a generalization of something you saw in Calc 1, which is the linearization of a function f of x at a point x equals c. And so you might remember that you have this formula, L of x is equal to f of c plus f prime of c times x minus c. And so let's look at the intuition for what this formula was doing. And so let's say that we have this arbitrary function, f of x. And then the idea was, well, maybe we can find a good approximation of the function f of x at the point x equals c with a line. And if we were going to do that with a line, then maybe the two things that we want to make sure are true are that the line actually goes through this enormous red point that I drew, and also that the line has the same slope as the function at that point. And so if I write that in terms of equations, what I'm asking for is that I want f of c to be equal to L of c. So in other words, the line goes through that point. And I also want f prime of c to be equal to L prime of c. Or in other words, I want the slope of the function to match the slope of the line at that point. And so if you just combine those two things and you use the formula y equals mx plus b and then match the slope of the line and the one value it passes through, then you could rewrite it so that you get this formula here. And so today the idea is going to be, what if we don't just stop at the value of the function and its first derivative? What if we want to have a higher order polynomial, and maybe we just want to match all of the derivatives of the polynomial with our function at the point c, right? So the linearization just matches the original value of the function and its first derivative with a line. And we could just continue this idea for more derivatives. And so let's see how we could find out an appropriate formula that we could use to find a good polynomial to estimate f of x. And so the idea is we're going to pretend that we could write f of x exactly as some infinite polynomial, which I'll call a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, and so on. And so here we're pretending that c is some constant value like 2 that we know what it is already. And now the goal is to figure out these coefficients a0, a1, a2, and a3, and so on, so that we know which series is actually going to represent this polynomial best. And so here we're assuming that this function f of x can be written as an infinite series. This is a huge assumption, and it may not actually be true. And so we're going to deal with whether or not we can actually assume this sort of thing later on. But for now, we're just going to assume that we can write the function as an infinite series. And so now we need to figure out, for example, how to compute a0. Well, like I said before, we probably want the left-hand side and the right-hand side to agree when you plug in the value c. So if I just plug in c, then I can say that on the left-hand side, I just get f of c. And then on the right-hand side, every term just disappears except for the very first one. And so we can see that a sub 0 is just going to be equal to f of c. And so that's actually what we had for the linearization formula at the top of the page as well. And so now we'll take a derivative of both sides. And so by both sides, I mean of this equation here where we had f of c is equal to blah, 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 blah. And so then we're going to get f prime of c, or f prime of x, I'm sorry. And then on the right-hand side, when we take the derivative, the a0 term just disappears because that was a constant. The a1 times x minus c term, when I take the derivative with respect to x, that just becomes an a1. And then the a2 times x minus c squared, now I'm going to get 2a2 x minus c, and then plus 3a3 x minus c squared, and so on. And now, in order to figure out what a1 is, the idea will be, again, to plug in c. So if I plug in c into both sides, then I get f prime of c is equal to a1, and now all of the other terms just disappear. And so this actually matches again with the linearization formula, where now we've seen that the coefficient in front of x minus c should be f prime of c. All right, so at this point, you might expect that the next term would just be f double prime of c, and the next one f triple prime of c, and so on. But it turns out that that's not quite the pattern, and so we're going to have to do just a little bit more work in order to see what the pattern really is. And so if I take the next derivative, then I get f double prime of c is equal to 2a2 plus 3 times 2 times x minus c, plus the next term would have been a 4 times a 3 times an x minus c squared, and so on. And so now if I plug in c into this, then I'm going to get f double prime of c is equal to 2a2. And so in other words, this time I'm getting that a2 is equal to f double prime of c divided by 2. And so that divided by 2 is a little bit different than before. And so let me look at another one just to see what's going on with this division. And so if I take 3 derivatives now, then on the right-hand side I'm going to get 3 times 2 times a3. And so I could see up here, by the way, that I dropped the a3 and the a4 in that line right there. I'm sorry about that. But now that that's back in there, this should have been a 3 times a 2 times an a3, and then a 4 times a 3 times a 2 times an a4 times an x minus c, and then plus so on. And so at this point, if I plug in f triple prime of c, then I'm just going to get 3 times 2 times a3, because again, all of the other terms disappear. And so that implies that a3 is going to be equal to f triple prime of c divided by 3 times 2. Okay, so maybe at this point the pattern is sort of clear. You could see that the next term I'd get a 4 times 3 times 2 in the denominator, and then the next term would be a 5 times 4 times 3 times 2 in the denominator, or in other words, every time I'm getting a factorial in the denominator. And so if I try and generalize what's going on here, then I can see that a sub n is going to be the nth derivative of f evaluated at c, and then I'm going to have to divide by some factorial, and you could see from the examples that we've seen that it's going to have to be n factorial. And so if I go back and check that this makes sense for the examples we saw, a sub 3, right, that was the third derivative evaluated at c, divided by 3 factorial. A sub 2 was the second derivative divided by 2 factorial. A sub 1, really, I could say I was dividing by 1 factorial, and in fact this formula even works for a sub 0, because 0 factorial is defined to be 1. And so at this point we've seen what the coefficients would need to be in order for us to match the derivatives between my original function and my infinite series right here. And that'll help us define Taylor polynomials in a minute.